So we'll get into the background and setting of Erionite, then go into the investigation, and then kind of fast forward today on kind of where we're at. Because I will say, kind of from the offset, the Erionite kind of research is very ongoing, and there's always stuff that people are researching, which makes it kind of a challenge to keep up on what is the latest research, because there's always someone doing something about it. I know right now there's a big interest down in New Zealand because, I can't remember the town, but one of the towns, maybe Auckland, is starting to expand in areas they know they have Erionite. So it's not just this remote formation. This is a place they're actively digging formations or digging basements and foundations into Erionite-laden material. So some places it's a very active area of research. So anyway, so what is Erionite? So Erionite is a naturally occurring microscopic fibrous zeolite mineral. So this is something that you really cannot tell with the naked eye if something's got Erionite. You have to get it under a microscope, and you really have to get like scanning, some high definition microscopes to be able to even see the Erionite. And so in North Dakota, it's found in basically weathered volcanic ash deposits. And in a later slide, I'll get into more on how it was formed in North Dakota. Well, Erionite is characterized basically by an aluminum silica framework, which forms kind of all these cages, which then in these cages, you have all these extra cations that can fit within the cages. And it kind of varies, which complicates trying to say on what is the chemical formula for Erionite. There's a wide spread. So you could have, calcium, potassium, sodium, magnesium, and all kinds of different mixtures. And so what also makes this more complicated is ophrotite is another mineral, very similar. And if you just look from a spectra perspective, and I've got a paper if anyone wants to see it, the spectra for ophrotite compared to Erionite is almost identical. And so if you didn't know that, hey, you need to look a little more, do these different techniques to differentiate the two, you could think you just had ophrotite, not Erionite, and just totally pass right over it. So now some nice little pictures that I was able to find from some different research papers. So the one on the left basically has kind of the majority cation graphed on a trinary plot on various types of Erionites that have been studied around the world. In particular, the Erionite we have in North Dakota. So basically called the killdeer Erionite, even though we have, as you'll see, we have Erionite more than just in the killdeer area. But on this kind of trinary plot, what you want to look at, the red circles and the red squares are the killdeer mountain Erionites. And so you can see there's a pretty wide spread in kind of what those cations are. The little light gray diamonds and light gray squares, that's from an earlier study of kind of Erionites worldwide and compared them with ophrotite. So you can see those kind of gray symbols, they're much more bunched up in separate areas. So if you see, let me bring on the cursor. Erionite is plotted much more right on this side up here, where ophrotite was plotted much more right in the center. And this backs up some research that Nels Forsman did way back in 1986, where ophrotite was kind of mapped right here. But important to note, these little pluses here on the side, those pluses are the Turkish Erionite, and we'll get into a little bit later why those are important. But for right now, what you want to get from this is that the North Dakota Erionite basically covers kind of the widespread between ophrotite and what would traditionally be called Erionite, but it also crosses over into this area that matches the Turkish Erionite. So this makes it difficult to figure out if you've got Erionite or ophrotite, but in the big scheme of things, to know that this killdeer Erionite is very similar to Turkish Erionite is a big thing you want to remember. And then just kind of a nice little schematic I found from a paper that lays out what the kind of structure of Erionite looks like with all these cages. So you kind of have this central column right here of more tightly packed cages, and potassium you'll find in these kind of medium-sized cages. But these really big cages here on the side, that's where all the other cations are formed. So calcium, sodium, all that. And so you can see as with a cage that big, it's pretty easy for different elements to get in there, which makes it really hard to figure out, okay, what's in my Erionite? You have to actually do some study to figure out what's in those cages, because it could be all kinds of different things. And then next up here is just some simple maps of kind of where we know, based on previous research, Erionite has been found. And so a previous study back in '96 by Shepard kind of was one of the first ones to really map out where these are. And then subsequently, with kind of all the interest that the North Dakota Erionite spurred, there was more research done in many more locales. But I think we're pretty close to about 100 locations where we know Erionite to exist in kind of Western United States. So kind of the big thing is you want kind of a drier area, because like a lot of these fibers out east, if they exist, you're just probably not going to find them. Where out here, you have the kind of the drier conditions where these fibers are much more of an interest. So I would suspect that it's more widespread, but unknown on just how widespread it is. And this next slide, actually, I'll jump into that. So kind of where this Erionite comes from. So for us, basically, main formations you want to look for are the Rickery, Brule, and the Shadron. I hope I'm saying those right. But basically, a volcanic ash was laid down, and then through various weathering processes, all that ash was concentrated in lake bed sediment. So you get these nice tough layers. And then as that tough layer is altered, you have the zeolites form in little cracks, little vugs within that tuff. And so it's not necessarily the volcanic ash itself that's the problem. It's these zeolites, these secondary formations that formed once it's been weathered. So like if you had a fresh ash, you wouldn't have these zeolites yet. So that's one of the things where you kind of need multiple steps. You can't just have the ash. It has to be weathered as well to start getting these Erionites. And so then a map on the right shows southwestern North Dakota and shows kind of the known areas. So the big areas we have is around Killdeer, up in Dunn County. Bring pointer back on here. So Killdeer Mountains are about right here. And so you can see the deposit kind of extend down there. And then the little Badlands southwest of Dickinson, and then White Butte area and Slope are all areas where we know Erionite to exist. And then we've got some samples from Little Buttes scattered around that we've either confirmed Erionites in or we suspect because it's got the same formations in it. But then you ask, well, why do we care about Erionite so much? What's the big deal? Well, and there's some backstory to this, which if you ask me about, I can probably talk an hour just on why this became a big deal, but I'll save that for later. Suffice to say that back in the 1970s, there was discovered to be a high incidence of malignant mesothelioma in Cappadocia, which is in Turkey. So basically think central Turkey. And so one of the big things is mesothelioma is pretty rare unless you have like obvious asbestos exposure. So people that deal with asbestos a lot, there's quite a bit of mesothelioma. But beyond that, like general population, very low, like 0.00 percentage points. Some of these villages in Turkey were having mesothelioma rates of almost 50%. So basically half of the deaths in these towns were attributed to mesothelioma. So that raised some big flags when these researchers found this, because you just don't see those kind of numbers naturally. So when they went to these villages and started looking around, they noticed, and you can see it from these pictures, that people were using kind of the rock material, not just as like road material. You can see the rocks that they've made this road out of, but they're digging into it for their homes. So they are interacting with this material on a 24/7, 7 days a week basis. All their lives are spent around these rocks. And so with this kind of very apparent geologic feature, these researchers started looking at these rocks like, well, maybe these rocks are the problem. And what did they find in the rocks? Erionite. And so with that, they started to do a bunch of health studies and found that this erionite is very carcinogenic, much more than asbestos. And so they did various, lung tissue studies, animal studies, all kinds of different medical studies. And basically this resulted in erionite being classified as a group 1 carcinogen, which a group 1 carcinogen is basically known to cause cancer in humans. So it's not a maybe, it's, yeah, we know it can cause cancer. And why, for those that don't know what, mesothelioma is, especially malignant mesothelioma, why that's so important is because basically from diagnosis, you have about 1 year alive left from diagnosis. So it's not something that you can have mesothelioma, for maybe 5-10 years. It's, once they know you've got it, you only have about a year left. So it's pretty critical to diagnose this kind of stuff early on and get it treated, because it impacts you very quickly. So now fast forward to North Dakota. So they've known Erionite's been a problem for a while, but it was never connected that, oh, there's this Erionite problem in Turkey. Oh yeah, we've got Erionite here. Until a very, I'd say, lucky geologist out at UND, I think he's still out at UND, and I won't name names, but basically he heard a presentation on Erionite at UND. And because he had mapped Erionite in North Dakota, knew we had Erionite as well, and so contacted the survey, who had also done work on mapping Erionite. So the survey got very interested in it, which then led to kind of this snowball effect of all these other agencies getting involved. Because, hey, if Turkey has these villages where 50% of people are dying of mesothelioma, what are our towns and Southwestern North Dakota facing? So at the time, so I'm part of the Department of Environmental Quality, but at the time we were still under the Department of Health. But basically we got pulled in since Department of Health, and then with the survey's help, when we called in the US EPA, who then called in the US Geological Survey. So kind of these all big agencies came in. And first we wanted to look at, okay, we know we've got Erionite. The survey's done work, other people have done work mapping out where we know kind of the big locations of Erionite are. How widespread is it beyond that? But then how much of this Erionite that we know is in the rocks is actually getting airborne to where the public can be affected? So basically breathing it in. If it's just in these little isolated pockets, maybe it's not a big deal. But if the community is being exposed to it, on a daily basis, then we need to know. And so we started taking bulk samples of the soils and gravels, not just in the formation, but also in the nearby community. So Killdeer was kind of the main staging area where we took samples from the roads, the parking lots, and even inside buildings where dust from the parking lots would come in. So seeing, does that dust have Erionite? Is dust Erionite being brought into locations you wouldn't expect? And then there was some other samples taken in 2009 kind of back this up. So the time frame you're looking at here is about from 2006 to about 2010. And so here's a picture of some of the work that was done. So picture on the left is one of the formations that has those altered volcanic ash layers. And then on the right, I believe these are US EPA contractors taking samples of the Erionite rock. And then these are kind of some of my more favorite pictures, because these show the air sampling. So I just, I'd like to go back in a time capsule back to Killdeer just to ask people what they thought of these guys almost in hazmat suits sweeping the gravel what he thought of all this, because this was kind of one of the things they had him do is, manipulate this gravel to see are any Erionite fibers being made airborne. If there's Erionite in the rock, but it's not becoming airborne, people can't breathe it in, so it's really not a healthy risk. But if it is being made airborne, then we have a problem. So then we'll get into the results. So this is kind of a busy graph, but it's very good in that it kind of contains all the information from those collections. So on the left shows kind of all the different situations they were doing. So I will point out when it says ABS, that is basically activity-based sampling. So they were manipulating the gravels. Where the stationary is they just had a sampler set up to take air samples. So, from my mind, I would think the activity-based samples, as you're disturbing it, would cause you to have more detections, you'd have more Erionite, versus the stationary. When I think these fibers, I would assume they would settle out and you really wouldn't get any samples. Well, if you look kind of at the center, say right column, the number of detections, you see that you get detections of Erionite basically no matter what you do. Whether it's stationary or whether you're actually disturbing it, there's Erionite everywhere, basically. So inside the buildings, out in the parking lots, on the roadways, they're catching Erionite fibers in almost every situation. There's just basically one method in one situation, this indoor office activity-based sampling, where they didn't get one. But it's only a sample size of one, so it's like, but don't hang your hat too much on that. So with that, we basically knew that, yes, we've got Erionite throughout the Killdeer area. It's there, it's in the air. Now, what do we do about it, and how much of a problem is? Because we knew kind of just anecdotally that there didn't seem to be a big mesothelioma outbreak, because we do have like cancer tracking, and assumedly we would see something if we had 50% of the people dying. We would see something like that, but we had not seen anything like that. And so kind of what's going on? Why is our Erionite seemingly not affecting people? Maybe it's just not had enough time. Because one thing I didn't mention about like mesothelioma and kind of how it forms is it takes a while. You're talking about maybe 30 to 40 years from exposure. So it's not something that you get exposed to it and then the next day you're showing symptoms. I mean, it can take decades for it to actually show up, and something that you really need kind of repeat exposure to it. So maybe it's just not been long enough for the people in Killdeer. So with those kind of questions in mind, the next step was to do a medical study. So again, kind of the same agencies involved, Department of Health, then the US EPA, and then we had, I'll have to look at my notes, the Agency for Toxic Substances and Disease Registry. They all partnered together, and we pulled in the University of Cincinnati's College of Medicine to basically do a whole toxicology review, statistical cancer analysis in the area, and basically try to figure out what are kind of the toxicity of Erionite in the Killdeer region. So what was done was basically after we had screened a number of people in the Killdeer area, we focused on high exposure occupations because we figured if you're exposed to these gravels on a pretty regular basis, you should logically have more of an impact than, say, someone who just, works in an office away from the gravels. But unfortunately, if you're familiar with Dunn County and Killdeer especially, there's just not a whole lot of people there. So when you start to look at these high exposure occupations, we only got about 34 participants. And there are various people that were, removed for things like, because some people interviewed did have previous asbestos exposure from previous occupations. And I'll show you a picture of one of those individuals later. But with those 34 participants that were selected, there were x-rays and the high resolution computed tomography done. And that's kind of an important thing. X-rays were not really good for detecting whether or not they had Erionite like damage to the lungs, because what we found out is kind of what Erionite does to the lungs is it damages kind of the outer membrane, kind of the layer between the outside of the lungs and then the inside sac. And you can't really see that on x-rays. But the high resolution computed tomography takes cross sections, and I'll show you some pictures coming up of that. And you can see these kind of abnormalities very clearly on it. So it's definitely something that the HRCT was much more expensive, much more harder to use, but it was basically the only way you could figure out if there was any changes that could be attributed to Erionite. So then going into kind of the results of it, in 2 participants, so 2 out of the 34, you could see that there were changes basically to that membrane within the lung. But when they did kind of a statistical analysis of the cancer rates in the region, there wasn't an increase. And so you have these 2 individuals that you do see changes, but on a population level, there doesn't seem to be an increase. So again, raises the question, well, is our Erionite just not toxic, or just has it not been enough time? There's still a lot of questions there, which I'll get into in a later slide. So next, we'll go through some of the slides showing those HRCTs, because it's kind of interesting to just see what this looks like when you're looking inside a lung. And one of the things I'll say is, like, I'll preface this, is we don't necessarily know that these changes are Erionite based, because my understanding from talking to people about this, to actually determine whether it's Erionite or not, you'd have to do a lung biopsy. And to do a lung biopsy to someone who's living is not something you want to do. So it's one of those, like, basically until someone's deceased, you really can't know for sure if this is Erionite related or not. So this first photo here is basically a healthy lung. Bring the pointer on here, because one thing we'll be looking at is basically what you're looking at. This membrane is kind of this outer layer right here. And so, like, the things in the center here, these are your organs. Again, this is a geologist trying to explain medical terms, so I apologize. But, you want to keep an eye on kind of this outer layer here is what we're looking at. So this first photo here is one of the 2 individuals, and you can see most of this layer is pretty smooth. But then you see, and it's kind of pointed out with these little arrows, you see these little bumps here. And so that's kind of the signs that, something is irritating this membrane and causing, this scarring to occur. Then here's a picture of the second individual. Again, you can start to see this build up here along that layer. So it's not mesothelioma yet, but, could be the start of it.
What is the buildup? What's it building up with?
So the scarring, so basically something is in there irritating it. And I'll talk about it kind of on a later slide. So one of the things that a lot of things that can cause cancer don't necessarily do it right away. It's when it sits there and continuously irritates the cells. Like, a cell's not going to become necessarily cancerous right away. And again, this is a geologist trying to explain medical stuff. But as I understand it, is you really need repeat damage to start to get those cells to mutate and become cancerous. So that's why, like, these deposits sitting there, it's not something you want, because you want the lung, when it gets irritated, to be able to kind of get rid of that stuff. But I'll talk about it. There's an issue with Erionite in that process. So this is the last one I'll show. And so this was one of the individuals that was removed from the study. So if you can see, there's much more. There's large kind of buildups on this. So this individual had previous asbestos exposure. And so that's why, even though they also had a very long time frame in dealing with rocks that probably contained Erionite, couldn't discount that maybe this is just asbestos. So again, it's like without an actual lung biopsy, you want to be able to tell. So getting into kind of the findings and initial conclusions from both the geological study and then the medical study. So air sampling revealed that there is Erionite in the Killdeer area, or at least was back then. And then in these concentrations, when they compared them with the concentrations in Turkey, were found to be similar or greater than the concentrations in Turkey. But interestingly enough, the fibers here that we were becoming airborne were shorter and thicker than the ones in Turkey. And I will say, I gave this presentation last year and I mixed that up. I called the fibers longer, but they're actually shorter, and it will make sense in one of the other slides, because for these kind of asbestos and basically these fibers that can cause cancer, you need the fibers to be kind of long enough to irritate the lung. But if they're too thick, then they can't get deep enough into your lungs. So you want them to be long, but you want them to be thin. And so this kind of helps the idea that, well, maybe our Erionite isn't as dangerous because it's short and it's thick. So it possibly can't get as deep into the lung. However, based on the medical study, we saw that 2 individuals that had high potential, high exposure to Erionite rocks did have changes to their lung tissue. But statistically, there's not, and this kind of, I'm glad, but it's hard when you have kind of all these different pieces of information, because statistically there's not an increase in mesothelioma in the southwestern portion of the state. So with these kind of conflicting data points, the Department of Health, along with the Department of Transportation, kind of issued a better safe than sorry recommendations, which basically said, do not use this rock. And those recommendations are actually requirements, where for DOT state projects, you cannot use any rock that comes from an Erionite area. And so if basically the pit tests positive for Erionite, you can't use it for a state project. Doesn't mean you can't use it for anything, but just for state projects, you can't use it. So getting in kind of the current research and the challenges for this. So beyond just the fact there's a lot of differences between our Erionite and Erionite you find other places, the toxicology and kind of the hazard that it represents is very difficult to quantify, because you have all these different variables. You have just the chemical variability. Maybe I have more sodium, maybe I have more magnesium, maybe I have more, just various different cations in this chemical structure. Maybe that changes the toxicology of this Erionite. But then you get into the aspect ratio. My fibers, these Erionite fibers, are too long or too short, too fat, too thin. And then maybe people think I have Erionite, maybe it's just ophrotite. Maybe I have an ophrotite that I'm pretty sure is ophrotite, but maybe it turns out to be Erionite. So a lot of confusion on what am I actually looking at when I'm trying to study this stuff. And then biodurability. So one of the big things about Erionite is it's very durable. So when it gets into the lung, so for some asbestos fibers, like there's some asbestos fibers that basically they can be, once you get them into your lung, about 90 to maybe 150 days, it'll be gone. Where Erionite fibers, the one research paper that looked at how long it lasts, came up with a number of 181 years. So once Erionite's in you, it's very durable. It's basically going to be there for the rest of your life. And then you have iron impurities. So the iron impurities is kind of a research area, because we know that iron causes a lot of redox reactions with tissues. And so maybe it's the iron impurities that are found on a lot of Erionite samples that make it so deadly. An area of current research. So this all lays kind of the mechanisms of toxicity, the mechanisms of exposure, and then genetics. Maybe some people, in these Turkish villages, one of the areas of study was maybe they have a genetic, difference that makes them more susceptible to mesothelioma. So basically what all this means is that all this research that's been done, the US EPA, there's still not a federal limit on what is a safe level of Erionite. No one knows. Where asbestos, we have set limits, but Erionite, there's nothing. So which makes it very hard for me to be able to say, well, can I use this Erionite or not? I don't know. Well, I've got a slide that kind of helps with that. So while I gave this presentation last year, just a couple months ago, I had basically that exact question raised to me, is because someone in an area we know Erionite existed really wanted to dig a gravel pit. And so trying to convince them that no, that's not a good idea. I found a paper that just happened to be published on April 7th of 2024. I'd say, I don't know if they knew I was struggling and published a paper on my behalf to help me or not, but basically it's kind of gave me a clue that kind of helps me say, what to do with this Erionite. So basically what these researchers did, and they're basically risk assessors. So they're not necessarily researching Erionite, they're taking all the data that's been published and then trying to come up with what is the potency for mesothelioma from all these different Erionite fibers, and then comparing it with the asbestos fibers as well to figure out, is Erionite really worse than asbestos? Is it not? That kind of thing. And what they did was there's this equation that was published back in 2019 by Korchevsky. Hope I say that name right. But that came up with kind of a potency number. And so these risk assessors took this equation and took all the information from all the Erionites and asbestoses that they could find in the research papers and came up with all these mesothelioma potency numbers. So this is kind of this picture here is kind of the big synopsis of that. And so the one on the left I'll concentrate on first. So what you're seeing is the mesothelioma potency is the vertical graph. And then the x-axis, kind of the horizontal, is the aspect ratio. So aspect ratio, remember, is kind of the length versus the width. And so for the North Dakota Erionite, if you can see, I know it's hard to read this, we're in the very bottom here, right, kind of the lowest number here almost, with a 0.2 kind of mesothelioma potency. And that's one of the big things, is because the aspect ratio is so low, because our Erionite fibers are so short but so thick that the potency, they think anyway, is pretty low, versus some of these aspect ratios for Erionites, say out in California, where you can have much higher. And I'll say the Turkish Erionite, I think, is somewhere, around 11 or so. But I'll say, like, one of the things to point out, like, why is there so many different aspect ratios for, say, California and Nevada and Arizona? They gave a wide range of different aspect ratios for ones where the research didn't specify. And so for the killdeer Erionite, the research that had been done nailed down pretty accurately what the aspect ratio was. So our aspect ratio is about 5.8 or so. And so they knew we really didn't have any, long fiber Erionites in the killdeer area. So that allowed them to kind of narrow down the mesothelioma potency factor for the killdeer Erionite. And so that's good news compared to other Erionites. It seems like the potency, based on this anyway, is kind of one of the least, one of the lowest of the Erionites kind of around the world. But then you kind of have to back up, and that's why I'm glad they included asbestos, because if you compare it here on the picture on the right, here is the mesothelioma potency compared to asbestos fibers. And so you see there's some asbestos fibers, so the crocodilites asbestos, so those have a higher potency. But then you look at some of these other, so like I know chrysotile asbestos is kind of the least potent. And you see that our kind of 0.2 is above that, but below some of the more hazardous asbestos fibers. And so kind of what I take from this is our Erionite compared to other Erionites may be less potent, but compared to asbestos, it's still potent. And, if you care about asbestos, then you care about Erionite, basically. So with that, and I'm trying to keep my talk short to take in questions, but I know I'm still probably going to run a little bit long. But with that, I'll get into questions and discussions. And I skipped over quite a bit because there's still I could talk for hours about this, but I'll kind of leave it up to people with questions to get into more detail on things. So I guess I'll start off with what questions you guys might have.
Just out of curiosity, did you like measure Erinites and Bismarck just to see if you measured any? Is that control?
No, because so this was all back kind of before my time, but my understanding is they only did kind of the air sampling for Erionite in areas where they knew it would exist, because again, like you need the fibers to stay intact. You know, if say I had an Erionite gravel stuck to my tire, you know, going out to the oil patch and then driving back to Bismarck, the odds that that fiber would survive the trip on I-94 back there, just as it breaks down, you know, it's no longer respirable once it's so small that it can't get into your lungs. So no, to my knowledge, there's been
So
no.
there's no way that they could really know. You'd have to get false positive, I guess what I'm getting at.
Well, there's a whole lot of. So one of the questions was basically, have we done any Erionite studies on areas outside where we know Erionite exists? And it's one of those, I think, one of the big challenges, it's so hard to study. And I'll show you a paper kind of once these questions wrap up, but it like Ophrotite especially is almost identical if you're kind of using the wrong technique for it. And also, as you're analyzing Erionite, you'll damage the fibers. And so you can't even really study the same sample twice. Once you've kind of analyzed it once, it destroys that Erionite. And so trying to reanalyze it, there's so many complications actually studying Erionite that makes it trying to, you know, with confidence say there's no Erionite in all these other areas. Real sketchy. So it's like, I understand why they did it here, because they know there's Erionite, because it's been, you know, you can see it. But for areas outside of it, trying to say, is there Erionite in these areas or not? You know, gravel can be transported a long way. So it's not, you know, unreasonable to think some areas outside Killdeer and, you know, Little Badlands probably has Erionite-laden gravel in it. Any other questions?
What in the volcanic ash is altering to Erionite?
So it's water. So water is altering the volcanic ash, and for the exact process of the alteration, I will pass that on to the Geological Survey to explain that, because that is beyond what I could figure out.
So with asbestos, it's like a 30 to 40 year latency period from exposure to developing mesothelioma oil.
For Erionite, yes. For asbestos, I don't know the exact, because there's there's a lot of different asbestos fibers, but only 6 are regulated as actually cancer causing. So with all those 6 different fibers, my understanding is all those different fibers have different rates, but generally long term. So maybe down to 20 years, but definitely not something like in a year or two. We're talking decades. So whether it's 20, 30, 40, 50 years, you know, multiple, something that it makes it difficult to say, oh, you had this, you know, you got it from this exact place. So Benjamin, how do I see if there's questions for?
No one's posted.
Okay.
You can ask.
Yeah, if anyone online's listening and has a question, feel free to hop in.
Okay. There's one. Have similar Erionite related health studies been done in areas such as San Bernardino County?
So I actually looked up where that, so going back, so I looked up where that was, because for me, like, I don't know California that well, but San Bernardino sticks in my mind as there are people there. But when I looked up where this location was, it was very isolated. So I'm trying to get back to that map here. So if you see some of these locations down there, pretty darn remote. And I think it's Nevada DOT actually allows some rock to be used that has Erionite in it, because the locations this gravel would be used in is just so remote that the amount of exposure would be pretty low. So I would guess that, and to my knowledge, there hasn't been any studies. If anyone knows of a study let me know. But my understanding is in areas where there's just really no population, there's been no health studies on. which kind of complicates it because, you know, you really need a big enough data set to be able to, you know, one or two individuals living in the area really doesn't tell you much. You know, if one gets mesothelioma, you know, that 50% is like, it's not a reliable, robust data set. Now, there has been studies that has confirmed outside of Turkey. So there was down in Mexico, there's I think a farming community where the kind of the soil has Erionite in it. And they confirmed that Erionite-based mesothelioma was found in a couple individuals. And then I think there was another, you know, somewhere else nearby, can't say it, can't remember where, but basically there has been health studies in other locations, just not in the United States that I know of.
So it might be related to Adam's question, but there are some more limited discrete volcanic ashes older than those formations, like one in the Sentinel Butte, McKenzie County. There's one like the Marmouth ash in Hell Creek down by Marmouth. And, you know, people consider using that in concrete or something and make that a big deal. But, you know, if there was any sampling done on older ashes and maybe those are a completely distinct mineralogy of the ash and they're, you know, totally unrelated, but everything you know of is probably focused on that Oligocene, Eocene, Miocene stuff.
Yeah, so the question was, we've got a lot of other volcanic ashes, you know, is there basically any Erionite risk from there? And I'll say, I don't know. So it's one of those, like, based on previous studies that have done, you know, we focused on the layers we knew had Erionite in it. And, you know, one of the key things is it just, at least for our Erionite, while there's, you can get Erionite, so we have Erionite, there's kind of where Erionite was kind of first discovered was out in Rome, Oregon, and they called it woolly Erionite because it was very kind of, it looked like kind of tufts of wool. And so a very different structure than the Erionite we've got. But that Erionite formed in kind of a different mechanism to our stuff. And so if you think, you know, crystal growths like primary versus kind of secondary, where you get nice big crystals from primary growth versus the secondary growths we have, where it's kind of after the fact, you know, you're alterating these ashes and whatever little pockets exist, that's the only place you're getting it, versus a nice big area where you can really grow a crystal for a while. So, you know, I would say ashes that you know have been concentrated and then have had time to be weathered, you know, probably, I would assume, via water. I don't know all the formations, like mechanisms for Erionite, but I'd say you want that water alteration and you want those ashes to be concentrated. And so if you know of other places where that's happened, you know, that would be an area that would be interest to see, is there Erionite here? Because as you can see from kind of the picture here on the right, you know, there's a lot of areas that this can cover. And so, you know, with the long geological history North Dakota has had, this doesn't mean this is the only places. So, you know, luckily out east, at least most of the stuff's buried. But here in the West, where you have a lot of history exposed, there could be other areas.
We went back and looked at all, we had collected all these ash samples. And we looked and we didn't find it. And then I talked to scientists with the USGS who said that Erionite's too unstable, that you're not gonna find it in Cretaceous and Paleocene ashes. And we didn't, so.
That's the difference between 30 million years of unstable and
Yeah, that's what it, and it certainly proven.
Cretaceous, like late Cretaceous.
Yeah, because we looked at light ash, every ash that we've got, so.
Yeah, because like the blue bed up in Sentinel Butte would be about 50 something million, and Eurekary's, you know,
30,
25, 30.
No. So if you think you could just summarize
Right.
it.
So a quick comment that was raised by Ed Murphy was that they did analyze all the other ash or a number of the other ashes that they had and did not find Erionite in those. And so basically, according to the USGS, Erionite is unstable enough that you're not going to find it in really old ashes. So there's that.
Okay, one more question online. Did the Department of Health recommend a closure of any gravel pits in North Dakota where Erionite does not exist?
Yeah, so the one pit that they did sample heavily was closed. And so this was kind of the main test area because that's, where most of these studies come from. That was closed. However, and this is something that pops up every so often, is that, without an exact like exposure level, kind of what is safe, if there is a safe level, we've not issued a blanket do not use this because there could be certain situations, where this gravel could be used without exposing the public. And so we don't have a blanket exemption except with the DOT for these state road projects, because we know if you're using it in a road project, the likelihood that A, you're going to disturb it, and B, make it airborne. Like I've gone down enough North Dakota dusty roads to know you can breathe in a lot of stuff from these roads. So, for that's prohibited. They can't do that. But we don't discount that there may be some use somewhere that, it's kind of like asbestos. If you mess with it, you're risking the public health. But if you don't disturb it, your risk is pretty low. So that's kind of the better safe than sorry. So, I don't say you have to avoid it, just don't disturb it. Don't grind it up and don't breathe it in.
So online said in the Eriniquary, the BLM closed gravel pits in Carter County, the extreme southeast part of Montana, after testing confirmed Erionite presence.
Yeah, and that's, makes sense because it's one of those like, especially for, areas that you just don't have much population in, I understand, I can't remember again if it was Nevada or Utah that does allow some Erionite to be used, but like without a level to know what's safe, I just would say don't use it.
Areas where it exists, is there any recommendations for like filter sizes or particle size that you need? I know at the beginning you had particle size a little bit on there, but is there a filter that you need to?
Right. So the question that was asked is there a type of, personal protective equipment, kind of a filter you could use? And so kind of the problem with Erionite that, just coming straight out of the rock, it's too big to be respirable. It's not big enough to be able to breathe it in. You need it to be basically mechanically weathered down to a size you can breathe in. And so it'd be one of those that, I'd say if you're just picking up a rock that's got Erionite, you probably don't need any protection because there's no dust there. But if you're driving down a road, then, the size that's small enough to actually get into your lungs, it's very difficult to get a filter that would stop a particle that small. Because, a lot of like face masks or whatever, they're trying to get the big stuff out of from getting into your lungs. Where this stuff, and that's kind of, if you're familiar with kind of the, air quality terms, the PM, particulate matter. They have PM10 and PM2.5. So PM2.5 is smaller than PM10. And there's much greater hazard from PM2.5 because it's smaller, so it can make it deeper into the lungs. And so that's why, like, once you weather down this Erionite and break it down to a smaller size, then it can get deeper into the lungs, and then it becomes much more hazardous. But then that makes it much more difficult to get a filter to actually block that. You're almost, blocking, making it so small where you can't actually suck any air through. It's almost just a solid wall for a filter. So that's why I like trying to say what type of PPE would work. Like one thing I could look up is like what these EPA contractors, because you can see in these pictures, they've got masks, they've got full respirators on, but like what type of mask they're using, or any of them have filters, because I don't think any of these people had air assist, so they were breathing the air. But I could look that up and get you what filters they use, but who knows if that, actually effective or not. Because again, we don't have an official standard, like safety level. So,
Hi, this is Sheila. I'm the industrial hygienist with the BLM. And usually P100 filters, the magenta colored filters, are adequate for particulate size down that low. So not just asbestos or Erionite, but a lot of different particulate matter down to that level that they are certified to do that.
hey Sheila, can you hear me?
Yes.
Because I know for Erionite, they were saying down to about the 0.3 micron size was the area they were concerned at. Is that the size that the mask will cover then?
Yeah, let me get you the data on that.
Okay.
I'll put it in chat.
Again, this is just a geologist trying to talk about it.
Is this stuff water soluble? Break down
So
time with exposure to rain or snow or?
One of the interesting things is, so it will break down pretty quickly, and that's one of the challenges in trying to study it, because, and I'll try to exit out of here real quick. Hopefully to be able to see stuff. Let's see. Oh, no. Back. Hold on. I got to end this PowerPoint real quick to show this paper. But basically, this lab that does a whole bunch of the asbestos research wrote a little paper kind of describing all the issues they had with trying to analyze Erionite. So this picture right here is just of all the very strong similarities between ophrotite and Erionite just from a spectra perspective. So you can see like the spikes, they're almost identical. Mm-hmm. Right. But just from prepping the sample, so the picture here is, I think, what they say. So 250 micron. And then once they milled it down to 75, you see that the fiber's pretty well destroyed. So just trying to prep the sample, you can abrade or weather this down to where basically it's not a fiber anymore. And so you could assume that it's not hazardous anymore. But trying to determine okay, I lay this fresh gravel down on the road, so the Erionite's probably too big to become respirable. Well, maybe in 5 years of use, now it's how you can't really say what rate at what level is the Erionite hazardous versus maybe a road that's been in use for 30 years. Maybe the Erionite's been completely destroyed at that point. But yeah, so long term, I wouldn't worry about this once it's exposed and once it's had a chance to break down, it will break down enough where it's basically gone.
So if this stuff's forming in weathered volcanic deposits, is that forming in situ? Because these, the Shadron, Brule, and everything are heavily weathered after deposition in place.
Yeah.
And it can also form after it's been eroded and transported into these gravels, and then they're weathering in place in the turn, more recently. I mean, yeah, it must be breaking down further there. So I don't know when that weathering, most of that's happening.
Right. So the question was, is more of this Erionite formation in kind of situ in the volcanic ash tufts, or is it more in the gravels, both? And my understanding is it's more in the tufts themselves. So you need kind of time for the ash to be weathered, and because the research I found specifically describes the Erionite forming within kind of the crevices, the vugs, the pores of the volcanic at the tuffs. It's not really talking about the gravels once, the float, that kind of stuff breaks off. The Erionite should already be in that.
Plenty of it surviving the transport.
Right.
Mechanical
Because again, as this rock breaks, basically, as you take this gravel, the gravel itself has already been contaminated with it. So it's like once you break it up further, then you're exposing more of that Erionite, making more of that Erionite airborne.
Yeah, we looked at, because we knew it was in the rocks, and okay, is it going to survive from the rocks into the pediment gravels, and then from the pediment gravels onto the road, and during that process, and we found the fibers on it in all three areas.
Yeah. So one of the comments was made that we found it kind of everywhere, and that especially, looking at the data they collected, I was kind of surprised that, they found Erionite inside buildings, basically tracked in by people inside the building. So this stuff that, it can survive, short term, long enough to get into places you wouldn't think.
Just interesting that it would be fine at 20 million years old isn't too old, but 60 million, 50 million is, too old. So it's interesting.
So they did post that the 100 filter means 99.7% effective or efficient for 0.3 micron.
Okay. Yeah. So there you go. No, I'd still say, don't assume you're safe,
Yeah.
Still PPE. PPE is not the most effective. Engineering controls of just not touching with it is the best, but.
Yeah, thanks.
Yeah. Thank you.
And anyone online, my contact's in the chat if you want to get a hold of me, and then I can get you a hold of Russell then.
Yeah, because I've got a lot of extra information that I'd be more than happy to talk about. Thank you.